Alright, let's do some position versus time graph practice now that we've had a chance to talk about the graphs and what they mean. Alright, so looking in this first graph here, we have position on the y-axis and we have time on the x-axis. Remember that position, or the change in position, which is displacement, is a vector quantity, so it can be positive or negative. That's why the x-axis is in the middle here. This represents positive displacement and this represents negative displacement. If it were to cross the x-axis on this side, it means that the object is moving in a negative direction or towards the negative x-axis. Alright, or potentially the negative y-axis. It doesn't actually tell us anything about the direction there, other than that it's negative. Alright, let's answer the first question here. What is the velocity of the object in this graph? Okay, go back to the definition of velocity. Remember that velocity is equal to the change in position, or displacement, over the change in time. The reason I keep saying or is this delta x stands for change in position, and the change in position is what we call displacement. Alright, so it's actually not correct to say change in displacement because displacement is change in position. Alright, anyway, so this is your definition. So the velocity then is how much is the position changing over time. So here's your time, and how much is the position changing over that amount of time? It isn't. Very good. So the velocity of this graph here is 0. Remember, on 0 you don't have to put any units, and it's proper not to put any units. Alright, so now here's a real world question. What's the object doing? If it's got 0 velocity, what's the object doing? Very good. It is at rest. Okay, here's another question. Since the line here, or since the slope of the line is linear, what can you tell me about the velocity of the object? Very good. It is constant. Okay, let's look at the next graph. Again, this is a displacement versus time. We're in meters here, and our origin is right there. Okay, so what is the average velocity from 13 to 20 seconds? Alright, let's write down our formula. The average velocity is equal to the change in position over the change in time. Alright, and let's go get our points. At 20 seconds, the position is 8 meters, so we can write that down. And at 13 seconds, the position is at 8 meters. And then we can write in our x-axis information. Alright, so 8 minus 8 is 0 meters, and 20 minus 13 seconds is 8 seconds. And that gives us 0 for our velocity, which makes sense because we have a horizontal line here. So hopefully you've noticed that anytime you have a horizontal line on a displacement versus time or position versus time graph, the velocity at that point or range of times is 0. So the object was at rest here. Alright, so what's the average velocity from 5 to 10 seconds? Alright, again, write the same formula down. And this time, I'll let you figure it out. So, if you need more time, pause the video. Alright, so your answer may end up being a little bit different than mine. I said that at 10 seconds, which is right here, to me, it doesn't quite look like 6.5 to me. It looks a little less than that, so I chose 6.3. But, you know, it's obviously greater than 6. So I'm saying probably if you picked anything from 6.2 to 6.5, you know, you'd be safe there. Alright, so I picked 6.3 minus, and then at the 5-second mark, That does appear to me to be 2.5, but to you it might have looked like 2.8 or 2.7, anywhere in there. So our answers are going to probably be different because that's a little bit more arbitrary. The scale over here is not really conducive to looking at those specific points. So I came up with 0.76 meters per second. You may not have gotten that, but you should have gotten fairly close to it, at least 0.7 something. Alright? Okay, let's look at the next one. From 5 to 10 seconds, is the object getting closer or further away from its starting point? So here's 5 seconds, 10 seconds. Alright, and here's the object. Okay, so the displacement. Okay, here's where the object started at its origin. The displacement from 5 seconds to 10 seconds shows that the object's displacement, or its change in position, is increasing. Alright? It went from 6.3 meters, or excuse me, it went from 2.5 meters to 6.3 meters. Alright, there is some change in position here. Is that change getting closer to 0 or further away from 0? To me, that is getting further away from 0. Alright? So this right here, this is where it started from. If the object had been on its way back down to touch 0 again, then we could say that it's getting closer to where it started from. But this one is, here's where it started from, moving away from that. Alright, so this one is definitely getting further away. Alright, and then in terms of position, at 13 to 20 seconds, what is the object doing? It's not moving. Very good. So the object is at rest. Okay, cool. Let's look at the next set of problems. We're going to talk about instantaneous velocity now. All of the stuff that we've done previously has been for average velocity. Alright? But now we want to talk about instantaneous velocity. What's happening at a single moment in time, not a range of times. Alright, you'll see here the instantaneous velocity of an object is at some point or moment in its path. So here is our original line, this black line here. You'll notice that it is not a straight line, it's curved. What can you tell me about the velocity of the object that made this graph? Good. It is not constant. The velocity is not constant. What else can you tell me about it? Good. The velocity is increasing the whole time. Alright, so the object is continually speeding up as it moves. Or in other words, the amount of space that it travels for each second is more and more with each successive second. Alright, well, what if I said to you, I want to know what the velocity of the object was at exactly 3 seconds. I don't want to know from 2 to 5 seconds. I want to know exactly at 3 seconds. Okay? Well, what we're saying then is, or what we can say mathematically is, what if we took the average velocity of something, here's our formula for that, and what if we made the time here, what if we made that get smaller and smaller and smaller so that it got close to 0? Okay? If you look at an object moving, alright, here let's use my pointer here. Here's an object moving and the time is ticking along. Alright? So that was like what? 3 or 4 seconds? And we could put marks on the screen here and we could measure them and say, that that's 1 centimeter and that's 2 and so on and so forth, and we could actually get the velocity of the movement of the pointer if we took the time and we got the measurements. We could plug it into this formula and get the velocity of the little laser pointer. But what if I want to know how fast the laser pointer, what if I went like this? The laser pointer is going slowly and then it speeds up. If I asked you for the velocity of the laser pointer over the entire length there, you'd have to take into account this slow stuff and then the fast. That's going to give you a different velocity than what was the velocity at 1 second versus what was the velocity at 5 seconds. It was going way faster at 5 than it was at 1. What if I want to know what it was going at 1? Or maybe it started to speed up here at 3 and I want to know what the velocity was right then. Well, we can figure that out. If you make the length of time approach 0, if your length of time here gets really small and it starts getting closer to 0, then the displacement of your object is going to get smaller and smaller also. But the displacement won't be 0. So what we can actually do is use a little bit of calculus or pre-cal, and don't worry, you don't have to memorize this or know this, but we can say the instantaneous velocity, and we denote that by not putting the bar over the top, is equal to the limit as time, or excuse me, as delta t approaches 0 of the change in displacement over, or excuse me, the change in position over the change in time, which is equal to the average velocity. What this is saying is the instantaneous velocity is going to equal the average velocity if you measure the change in distance over a very small window of time. Alright? If you measured over a large window of time, we would get the slow moving and the fast moving all together. But if we start and stop our time very quickly so that it is an amount of time almost at 0, like 0.00001 seconds, then the instantaneous velocity is going to be equal to the average velocity over that short window of time. The way we do that in real life on this graph is by drawing a tangent line. A tangent line only touches the graph at one point. So right here, that is the point in time that I want to know the velocity of. Okay? Now you don't read over here. Remember, this is position. A lot of times y'all are going to want to just look right over here and be like, oh, that's like 18 or 19, so that's the velocity. That's not true. Remember, velocity is the change in position over the change in time. So if we draw a tangent line here, and let me see if I can't get a good color. If we draw this tangent line here so that it only touches this curve at this one point right there, and mine's kind of sloppy because of the length of the pen brush, we can get a linear line, which means that the slope of this line is the same all the way along the line. And the slope of this line is going to be equal to the slope at that one exact point. So we've drawn our tangent line and we've plotted some points on the tangent line here. And now we can plug those into our equation. We can say our first displacement, or our first position, is 35 meters minus 9 meters divided by 4.6 seconds minus 2 seconds. Alright, and that gives us 26 meters divided by 2.6 seconds, which gives us 10 meters per second. So, at 3 seconds, whatever object made this graph here as it was moving, it had a velocity of 10 meters per second at that one point. If you took the velocity here, it's going to be a velocity greater than 10, because this, if we drew a tangent line for this point right here, the tangent line would be steeper than the red line here. Alright, so it would have a different and a larger velocity. Alright, I think we'll leave it here for today. Thank you for learning with me, and I will see you next time.